Chapter 7, Lecture 3, Entropy. One of the goals during this lecture is to take a look at what's known as the Tds relations. These were differential changes in entropy written in terms of other properties. For example, this first equation, entropy is a function of U and V, then you can write these what's known as differential equations. On the second one, if entropy is a function of H and P, you can write this equation. The entropy change during a process can be determined by integrating either of these equations between the initial and final states. However, we must know the relationship between either du or dH and the temperature. So let's take a look at it for entropy change of liquids and solids. So liquids and solids can be approximated as incompressible substances, since their specific volumes remain nearly constant during the process. So if we take a look at the second relationship, if dV is 0, then this term goes away. So for liquids and solids, we can have a relationship that ds equals du over T. Du is the specific heat times dt. So since it's incompressible for liquids and solids, Cp and Cv are approximately equal. We'll call it C. So we can substitute back in that du is C times dt, then integrate between temperatures. And of course, the C value here inside the integral, one way we could do this is take an average value here. You know, if we knew what the C value was, we could certainly, as a function of temperature, if it was a polynomial, we could certainly integrate it in theory. But a quicker approach oftentimes is just to treat C as a constant, pull it outside the integral. So we'll take it like an average value. And then you end up with the integral of dt over T, which is obviously the natural log. So you end up with the delta S is equal to the average specific heat times the natural log of T2 over T1. Now if we have an isentropic process, that means delta S is 0. So in an isentropic process, you end up with that the temperatures have to be equal. So the temperature of a truly incompressible substance remains constant during an isentropic process. As an example, let's take a look at example 7.7, the effective density on a liquid on entropy. So liquid methane is commonly used in various cryogenic applications. The critical temperature of methane is 191 Kelvin, and thus methane must be maintained below 191 Kelvin in order to keep it in a liquid phase. The properties of liquid methane at various temperatures and pressures are given in table 7.1. In this example, we want to determine the entropy change of a liquid as it undergoes a process from 110 Kelvin and 1 million pascals to 120 Kelvin and 5 million pascals. We want to do this in two ways. We want to do it using tabulated properties, and then secondly, we want to do it approximating the liquid methane as an incompressible substance. Then we want to look at what air is involved in this process. So the figure here shows what's known as a methane pump. You have methane coming in at the bottom at a pressure of 1 million pascals and 110 Kelvin. The pump acts on it, does work on it, and pumps it out to a higher pressure of 5 million pascals and 120 Kelvin. So if we know what table 7.1, we have those values, the first thing we need to do is determine the properties at the different states. So coming into the pump, we're at 1 million pascals, 110 Kelvin. So we can look in the chart at 110 Kelvin, 1 million pascals, come across and we can get the entropy and the specific heat, Cp. We can do the same thing for state 2, 5 million pascals, 120 Kelvin. We can get the corresponding entropy and specific heat for that as well. And so we can directly apply the equation. Delta S is S2 minus S1. We could subtract the entropy values and we can determine it's 0.270 kilojoules per kilogram Kelvin. Now let's apply the second approach. Let's approximate the liquid methane as an incompressible substance. So here we need to find the average value for the specific heat. So we can look at our table again. We come across, we got 3.471 and 3.486. Just take an average value and determine the average specific heat, 3.4785. Then we can apply the, from the Tds relations, we can approximate the change in entropy as the average specific heat times the log of the temperature difference, which we know. So we get 0.303 kilojoules kilogram Kelvin. So the area involved is about 12.2%, which, you know, is a rough approximation. I mean, methane is not really incompressible. However, this assumption enables us to obtain reasonably accurate results with a lot less effort. Let's take a look at the Tds relations for an ideal gas. So here we can use the Tds relations, which I've shown here, and we can use either equation. So let's look at the first Tds relation. du is Cv dt. We have the ideal gas law, so we can substitute for du here, and we can substitute for P here and use RT over V. Now, of course, we can integrate both sides, and we can get the change in entropy is the integral from temperature here of Cv as a function of temperature, dt over T. And again, if we know what Cv is a function of T, we can actually integrate that. Or we could, if it's pretty much constant, we can pull it outside the integral. On the right, on the second one here, we just r is a constant, so you have the integral here. So that's just the log of v2 to v1. So you can integrate that out. So here's our first relationship we can use. From the second Tds relation, we can follow exactly the similar kind of process here. dH is Cp dt, and again we have the ideal gas law. We just have to solve for v here. Substitute in, and we get a similar result. The only difference really is we replace Cv by Cp, and we replace the V by pressure. So we can use either one of these relationships for an ideal gas. Now let's say let's use these relations as an approximation. So here we're going to assume that the specific heats are constant and pull them outside the integral here. So this first Tds relations simply becomes the following, and notice Cv becomes an average value, and we got the log T2 over T1. And then the second one is exactly the similar kind of process if you got Cp here. So you can use these relationships for an approximation for ideal gas. The book also gives us, so these relations are in kilojoules kilogram Kelvin. If you have the ideal gas on a unit mole basis, you can use the following relationships. I didn't derive those or anything, but they follow. So the only difference here is R, of course, is different, different value here. So here you can see, for example, a graph of Cp versus T. You know, so we're going to take, you know, if we know what Cp is at T1 and we know what Cp is at T2, we're going to just take an average in here. I mean, a much more complicated analysis would be to find the equation of this curve and actually do the integral. But oftentimes it's not, we don't have to go to the extreme. We're just trying to approximate it. So let's take a look at applying this approximation techniques in example 7.9, interchangeable and ideal gas. So air is compressed from an initial state of 100 kilopascals and 17 degrees C to a final state of 600 kilopascals and 57 degrees C. Determine the entropy change of the air in this compression by two methods. We want to use the property tables, property values from the air table, and we want to use these average specific heat values. So here shows the compressor. You have the pressure coming again at 100 kilopascals. The temperature is 290 degrees Kelvin. Remember here you have to convert the 17 degrees C to Kelvin by adding 273. compressor does work on it, and the air comes out at 600 kilopascals and 330 Kelvin. So remember, convert 57 degrees C, add 273, you get 330 Kelvin. This shows the process on a TDS diagram, state 1 and state 2. So using the air tables is, if you have them available, it's actually pretty accurate and also very easy. All you need to do is look up the values. So here at 290 degrees Kelvin, I've kind of highlighted what the different values are. You can see the value for S here. You can see the value for the the R value. You can get that out of the table as well. So and down here at 330, it's the same sort of thing. So you can subtract 1.79783 minus 1.6802 minus, this is the R value, the log of the difference in pressure, the P2 over P1. So you can find that the change in entropy is minus 0.3844 kilojoules kilogram Kelvin. So the second method here, you want to use the average value for CP. So again, you can approximate this using table A2B, which I've kind of cut here and showed you what it looks like. So there's not a value for 290 Kelvin, but we're going to use 300. And there's not a value for 330, so we're going to use 350. You could interpolate, but again, these values for CP are so close, it's not going to make a whole lot of difference here. So if you use the equation, the average CP value, what I did is I took these two values and added them up and divided them by 2. Got 1.006. Log of the temperatures minus R times the log of the pressures. So I got minus 0.3842 kilojoules kilogram Kelvin, which is pretty close to the first method. So it's not bad approximation.